Good. Okay, so it's a random variable. What type? Continuous or discrete? Just remind me. Discrete random variable, and it's something which happens at a constant rate. Yes. Yeah, happy with that? So if we have a random variable x, it can be sort of anything like tweets per minute, heart rate, or whatever. We distribute it using a Poisson distribution. What's the parameter that we use? Can you remember? Lambda, perfect. And that lambda corresponds to the rate. Can anybody remember the probability mass function? Perfect. Okay, now just like I said, you don't have to worry about remembering that. That is on the formula sheet. Actually, whilst we're here, and whilst I've got it open, I think it makes sense to have a look at the formula sheet. So in case you're interested, you'll have something very, very similar to this in the exam. So you look at the top, you've got the formula sheets there, okay? This is exactly the same formula sheet which you will get in the exam, okay? Now, like I say, I might reformat it slightly differently. I'm not sure yet whether I'm going to do it as a separate booklet or whether it's going to be embedded within the exam paper itself, but you'll have all these formulas in there. So if you scroll down to page 2, okay, you will see I've got a section on discrete distributions. I've got the binomial distribution and I've got the Poisson distribution. I've got how you should write the parameters of each of those distributions. I've got the probability mass function. So there's the probability mass function for the Poisson distribution. And on the top there, I've got the same for the binomial distribution. And I've also got the expectation and the variance there as well. Okay, so you can see it's pretty much all given to you. You happy? Yep. So like I say, that's all there, and it's exactly the same for the continuous distribution as well. Quick question. We don't actually look at uniform and exponential distributions in this course. I just realised there just wasn't enough time to put them in there. I was originally going to put them there. I usually introduce uniform distribution as a discrete distribution. It can also be given as a continuous distribution. Okay. Now, like I say, don't worry about that too much. I've kind of put it in the continuous distribution. It's slightly different. Okay, but it can also be a discrete distribution as well. Okay, but like I say, don't worry about that because we don't tend to look at it in this course, and it's the same for an exponential distribution. In case you're interested, exponential distribution is just the continuous distribution case of the Poisson distribution. Okay, but like I say, we don't tend to look at that too much. We just look at normal, binomial, and Poisson. Okay, so let's come back here. Let's go through question 3. So actually, there's not much more to do with this. We can make a start on normal distribution if we're all here next week. If not, we'll do it online. Okay. So, question 3, we have buttercups which are randomly distributed across a field with the probability of a randomly chosen square metre of the field containing precisely R buttercups being given by this. Okay, so we've been given that the probability that the number of buttercups, which let's say is x, okay, so x is the number of buttercups per square metre. That's our random distribution. Okay, that's our random variable. Okay, so we have the probability that x is equal to some value, so the number of buttercups is equal to r, is given by this formula. So it's going to be 2 to the power of r, e to the power of negative 2, all divided by r factorial, okay, where r is a discrete value which takes the value 0, 1, 2, 3, 4, etc., etc. Okay, positive integers, no, sorry, non-negative integers. Now, this formula here looks very, very close to this formula here. Would you be happy? Okay, so what's the difference between this one and this one? The lambda, what's the lambda? 2, absolutely. So actually I can get a bit more information from this. I know that x is going to be distributed using a Poisson distribution because the probability mass function is the same, okay, where the parameter, the rate, is 2 buttercups per square metre. Okay, 2 buttercups per square metre. Does that make sense to everyone, how we did that? Yes, how you extract that. Now, you notice that nowhere in the question does it say use a Poisson distribution. Yeah, it's expecting you to be able to extract that yourself. Okay, so you can kind of think about it as it's happening at a rate, like I'm having 2 buttercups for every square metre. So if I look at this square metre, I expect 2 buttercups. If I look at this square metre, I expect 2 buttercups. If I look at this square metre, I'm expecting 2 buttercups. So it is happening at a kind of rate. It is happening at a kind of rate. Okay. But also you can see from the way that I've constructed the probability mass function that it looks very, very similar. Are you happy with that? Yeah? So now I need to determine the probability that a randomly chosen region of area 0.5 square meters contains precisely 1 buttercup. Now, are you happy that in this case, I'm changing the area which I'm looking at? It's no longer going to be 1 square meter, it's half a square meter. Okay? So in other words, the rate is reduced by half. Yes. Okay? So I can define that with a new random variable. Let's call it y, because it comes after x. Okay? So y is going to be the random variable that represents the number of buttercups per what?
Per 0.5 liters.
Absolutely. Absolutely. Okay? So it's going to be half a square meter. You notice I have to define it as a new random variable because this random variable, it has that kind of embedded in it. It has that period, time period, area, whatever you want to call it. It's embedded within the definition of the random variable. So if I want to redefine this, I have to redefine the random variable. I have to get a new random variable. Does that make sense to everyone? Okay? So what do we want? We want the probability that a randomly chosen area of 0.5 square meters contains exactly 1 buttercup. So you want to find the probability that y, that's 0.5 square meter, contains 1 buttercup. Okay? Now just be careful here. How would I write the distribution for y? What is the parameter now?
1.
It's 1, right? How do you know it's 1?
It's half.
Exactly. It's half the size. Okay, it's half the size. So therefore, the parameter also has to be reduced by half.
Yeah.
Is it raining?
Yeah.
Really?
Yeah.
Oh. It was a nice morning this morning. So you notice that because you're talking about half the rate now, okay, the parameter also gets reduced by half as well. Is that okay? Good. So now you just simply use this formula here. Are you happy?
Yeah.
Simply use this formula. So okay, lambda is equal to 1. I'll try and speak above this. So 1. What is my x? What is my x? 1. Good. Then I've got that times by e to the negative 1, all divided by 1 factorial. Good. You can either stick this in your calculator, or you can just say it's 1 over e. That's the same thing. Yeah? 1 over e. Now, would you leave your answer like that? Would you leave your answer like this? Why not? It's meaningless, right? Yeah, absolutely. It needs to be given as a probability. Remember, we leave our probability as either a fraction, we leave it as a percentage, or we leave it as a decimal. Okay? This here, even though it is technically a fraction, is meaningless to me. I'm like, okay, so I've got a 1 over an e chance, right? It doesn't make sense to me. So convert this into a decimal. What do we get? 0.125. Now immediately I can see there's about a 12.5% chance of finding exactly 1 buttercup in half a square meter. Is that okay? E, the E button. Oh, okay. One job, honestly. 3, 6, 7. That's right. You're right. Yay. Good. Yeah. Now, if you don't know what E is, I have got a video online explaining it. We will also meet E again next term. Yeah. So it's part of the maths. Sorry.
I saw that video.
Is it good?
Yeah.
Good.